Hey, physics. Um, Back at it here. Still gonna be talking about waves for a little bit. I have a few more wave phenomena to talk about, so like some conceptual stuff like this. And then I do want to talk about some of the remaining equations down here on the wave section of the reference table. Talk about the electromagnetic spectrum in general here, and talk about, this thing down here, absolute index of refraction, has to do with one of the equations, obviously has to do with refraction, so I'm gonna take a look back at refraction as well. But let me start with the other two kind of like wave phenomena. When I talk about wave phenomena, I just mean like ways that waves interact with the things around them, right? Technically, there's a fourth one that we already talked about, wave interference, which is really when waves interact with each other. These are ways that waves interact, I guess, like with their environment. So we have wave reflection, we have wave refraction, we have the concept of wave resonance, right? So those were our R's. Um, Additionally, the next ones that I'm going to talk about, they both start with, or they're both D, right? So the thing I want you to be careful of, and I'll leave this on screen, refraction. Oh, that's uh, why are you the way that you are? Not you people, right? Computer. But refraction and diffraction. Right. Again, looks similar, sounds kind of similar-ish. Diffraction is a different interaction waves have when they reach a boundary. Right. Diffraction is when a wave reaches an opening in a boundary and passes through. Right, but it's not quite like refraction where it bends through. The visual for diffraction is very different from refraction. So now that I've taken the word difference out of this, I'm gonna take that picture out entirely. Diffraction is most commonly seen as like this is like a space between walls, or even the space like when you a door frame. Like if you open the door, there's just an empty space in between the two walls. So think of that as like the empty space in between two walls. This here is we and so I've always shown waves as up, down, up, down, up, down, up, down type thing. Think of these lines that I've just drawn, right? These lines that I just drew, think of them as the top of the wave. So instead of looking at the waves kind of sideways, we're looking at it from the top down. We only see the very top of each wave. That's what's happening there. All right. So the wave is passing through. The wave is traveling this way. It reaches a boundary. Now when it hits this spot of the wall and when it hits this spot of the wall, it's very likely that it will hit and reflect. It will just bounce back. However, this entire wave pattern is too big to fit through that little opening, and as such, it has to change its shape in order to pass through that opening. When it passes through the opening, what will happen is it will bend kind of like outwards, right? Now what I tried to do, and I didn't do a great job of it, but the spacing between the waves, the wavelength, right, doesn't change, but the shape of the wave, like it expands out, it kind of ripples out away from it. And that's what will happen with diffraction. This is why you can see light underneath a door, like if it's a dark hallway and there's a door on the side and you can see light spilling out. It's why it makes that angled pattern, and you can see the baseboard on the wall frame, even though the light like should just go out from underneath the door. Um, So like, again, if I look top down on a hallway, right, and there's a door here, and it's closed, but you see light. The light kind of glows out in a semicircular pattern, right? It doesn't, and you have to look for this, because the obvious glow, like, comes out like this. But if you look, the baseboard here in this section and the baseboard here in this section will also be lit up. It's very small, it's very faint, but the reason for it is this diffraction pattern. It expands out. It's almost like it's a piece of string and you're trying to pull it through, and it can only fit through that little itty-bitty middle section first, and it'll expand as it goes out. The smaller the opening is, the stranger, the more it has to kind of bounce out, open out, right? But diffraction, generally speaking, is when a wave reaches an opening in a boundary and it's able to pass through, but it has to shift its shape. The other wave phenomena is something that you have probably heard before or heard of before. It's the Doppler effect. I tend to call it like the race car effect, because if you think you've ever like watched or you've seen a commercial for a NASCAR race, you always hear "neow, neow." They make that noise, very specific noise when a car races by you, "neow." Right? It's a funny noise, but there's a reason for that noise, right? Car engines don't actually sound like that. If you're sitting in the car and you hear your own engine go "neow," you really should get your car looked at. But the reason it does that, right? The Doppler effect is an apparent change in the frequency of a wave as its source moves. So this is a perceived change. It's not a real change, it just looks like it changes. And what I mean by that, I'm going to draw a super simplified race car. Here it is. And it's going to emit waves in both directions. So here are the wave fronts that you might see, or that you might hear, right? Now, if our race car is moving this way, let's say that there is a person here, and let's say that there is also a person here. As the source moves towards you, it's emitting those waves and it's squishing the space in front of it. So the waves in front of it actually appear to be a higher frequency. More waves appear to be there, and you hear a higher pitched sound. Right, that's why you hear it kind of, the pitch goes up a little bit as it comes towards you. As it moves away from you, it stretches that space. So as it moves away from you, the frequency decreases. The frequency decreases, the wavelength expands. Moving towards the source, or the source moving towards you, there's an increase in frequency. Moving away is a decrease in frequency. There's an inverse relationship between frequency and wavelength, remember? So increase in frequency means a decrease in wavelength, the waves get smaller. A decrease in frequency means an increase in wavelength, the wave gets longer, right? But the Doppler effect is the race car effect. It's also the premise behind Doppler radar, right? Doppler radar sends out radar waves at very specific intervals. It sends them out in a pattern. And it fully expects to get that exact same pattern back. Now, these waves will pass through things until it finds something that it cannot pass through and it bounces back. So the Doppler radar also has a receiver. So it knows that this is the signal that's being sent out. Right? So it sends this out all the time. And it receives. So let's say if it received something that sounded like this, it's receiving a signal that's faster than the one that it's sending out, then that means that whatever it's bouncing off of is coming towards the tower. That's a system, that's a weather system that's approaching you. On the other hand, if this is the pattern that's being sent out, and the pattern that they get back, right, the wave patterns that come back are there's a much longer time period in between, right? The frequency decreased. That means that whatever that weather system is, it's moving away from you. All right. Now, the Doppler effect is also how a radar gun works for, like, if you're trying to a speed radar, right, for like a baseball team. If you're trying to determine the speed of a pitch, you point the radar gun and it shows how fast the ball is going. It sends out radar waves that are going a very specific speed, and depending on how fast or how slow they bounce back, they can tell the relative speed. So, diffraction, Doppler effect, two more ways that waves interact with their surroundings. All right. Now, I'm going to talk here about the electromagnetic spectrum really quickly, because there's some kind of curious things about all of these waves. These are all different types of waves, and these are things that we mentioned: gamma rays, X-rays, ultraviolet, microwaves, radio, etc. And then I'm going to get into, there are just two more equations down here, right here. N equals C over V, and this N1 sine theta nonsense, blah blah words and stuff. So we'll get into that. All right, but let me start here. And this is the electromagnetic spectrum, right? These are electromagnetic waves. They are energy. They pass from point to point. These are waves that do not require anything to move through, right? They're not like mechanical waves. Mechanical waves are things like sound, earthquakes. They require something to pass through. Sound needs air or water or solids, right? Earthquakes need the ground, magma. They need something to pass through. Electromagnetic waves are special. They can pass through just about anything. They can also pass through nothing. Now, in science, we refer to nothing as a vacuum. So electromagnetic waves are able to pass through a vacuum. The curious thing about all electromagnetic waves is that they all travel at exactly the same speed. They all go as fast as each other. So X-rays, ultraviolet, radio waves, microwaves, gamma rays, infrared, visible light, all of them travel at the same speed. They all travel at the speed of light, which is, on your reference table right here, 3 times 10 to the 8th meters per second, 3 million kilometers? No, 300,000 kilometers per second. So 300 million meters per second. It's real fast. Every single one of them, every kind of wave on the electromagnetic spectrum, travels at the speed of light. This is why when they take your X-ray in the dentist office, it's just a quick, very quick, click, click. You hear that little buzz, buzz, that's it. The reason for that is the X-ray travels very fast. You don't need to turn it on for very long to get a few X-rays to bounce back and forth and look at your teeth. All right, now X-rays are fairly high frequency. UV can be high frequency. Infrared is low frequency. Radio waves are low. Even microwaves are low, right? I don't know if I mentioned this before, but the reason that microwaves are dangerous, and the reason that your grandparents may have told you, like, don't stand in front of the microwave, is not because microwaves are like these super crazy dangerous, like, oh, they're high frequency, they're gonna mess up your cells. They're not. They're much smaller. They're a much lower frequency. They're a much longer wavelength. The trick behind microwaves is that there are just a lot of them in a small space, right? Your microwave oven is only so big, so there's just a lot of microwave in a small space. That's what makes it dangerous. It's quantity versus the quality of the wave per se. It's just a ton of them. So on the electromagnetic spectrum, on the left side we have high frequency. Generally that's more dangerous. It's able to pass through more things, right? So gamma rays are things that we said were dangerous. And as you go from left to right, the frequency goes down. It should also make sense that as you go left to right, the wavelength goes up. They have an inverse relationship. Everything here travels at the same speed, so if you tried to multiply them, you would always get times 10 to the 8th. The reason for that, again, is that they all travel at the same speed. Visible light has its own little cutout section down here. So visible light exists in this little itty-bitty space, right? Visible light goes from 7.69 times 10 to the 14th frequency to 3.84 times 10 to the 14th frequency. So if it's like, if you have light, or if you have an electromagnetic wave that has a frequency of 5.6 times 10 to the 14th hertz, it's visible light, right? If you look at the cutout section, I would turn this, but it'll resize it for me. If you look at the cutout section, you can see that there are very clear descriptions of which colors are which. And this goes roughly reverse order of how you learned rainbows. R-O-Y-G-B-V. Roy G. Biv, right? Indigo, you'll notice, is not on here. Really, violet doesn't have to be on here either. Roses are red, violets are blue. The color that we think is violet. Anyway. But you should notice that there are distinct frequency markers to designate in between these spots is this color. If you have an electromagnetic wave that has a frequency in between 5.2 and 6.1 times 10 to the 14th hertz, then you have green light. If you have an electromagnetic wave in between 3.84 and 4.82 times 10 to the 14th hertz, you have red light, right? If you adjust the frequency, I thought it was doing really well. Let's silence that again. If you adjust the frequency, you can adjust the color of the light, right? Now you can achieve this after the fact by putting a filter on it, but if you could actually adjust the frequency of a light source, then you can change the color of the light. Red to orange to yellow to green to blue to violet. Right? If you get higher than this frequency, higher than violet, you get ultraviolet light. If you go lower than this frequency, so lower than red, you get infrared. Ultra means higher, infra means lower. Those are literal terms. Now, something to recognize is that many of these ranges overlap. There's an overlap between infrared and microwaves. There's an overlap between ultraviolet and X-rays. So be careful if I ask you to identify a certain frequency or a certain wavelength, and just know that there may be multiple answers. Right? But the electromagnetic spectrum, these are waves that are pure energy, like all waves. They transfer energy. But they're unique because they all travel at the speed of light, and they are able to pass through a vacuum. They're able to pass through space where there is no matter. Alright. So, next thing, and last thing I'll do, this will be a shorter than an hour video, but still longer than average video, I guess, is looking at what this index of refraction means, right? This is by the way, this word is just the plural of the word index, right? So the index of refraction, which is here, it's labeled as lowercase n. This is a measurement. It's just a number, right? There are no units to this number. The index of refraction is simply a number. But the index of refraction is representative of how much does this material cause light to slow down. And this is what happens in refraction. This is why refraction occurs. I said, right, if you remember, my definition for refraction was when a wave reaches a boundary and it bends through. The reason that it does this, the reason that it bends, is because it slows down. Its actual velocity slows down. I said light moves 3.8 times 10 to the 8th meters per second in a vacuum. However, it moves at different speeds in different materials. So when you look at light as it passes through water, it's moving slower than the speed of light. Slightly. Not a ton, but enough. enough slower that it doesn't follow the same path it was going to, it bends. All right? Now, in order to calculate what is the speed of light through one of these specific surfaces, we have a formula here. Right? It says that n equals c over v. Right? So this, oh, nope, okay, I need to, I zoomed in. Okay. How to solve for the speed of light outside a vacuum. Right? The speed of light differs when it gets outside of a vacuum. This speed here, this v, is the speed of light through a specific material, right, through blank. C is the speed of light in the vacuum. That's never going to change. However, you should notice that all of these values are greater than 1. And the reason for that is because the speed will always slow down. So the bottom, the denominator, is always going to be less than the original speed of light, which means that when you divide it, you'll always get a number greater than 1, because you're making the number bigger. Now, the reason that light slows down through these objects is a little more complicated. The short version is that the particles of the substance get in the way of the pattern of the wave. So it slows it down. Most objects have different different indices of refraction. There are 2 objects that have the same index of refraction. 2 of the materials on your list have exactly the same index of refraction, right? I'm trying to find them because, like, right now I just am struggle training. Ah, there they are. Corn oil has an index of refraction of 1.47. Glycerol has an index of refraction of 1.47, which means that in both of those materials, in both of those mediums, light will travel at the same speed. I should have been more specific, but I was just trying to get the concept down. Looking back to refraction, this is when a wave hits a boundary between 2 different surfaces and it bends through. Right? And I should specify different because if you have like 2 pieces of glass right next to each other and it's the same type of glass, even though there is a boundary between the 2 pieces, that's really just one big material. It's one big medium. That's just glass. So it was a little unfair of me to say that before, but now, right, I can specify. Specifically, refraction is when a wave reaches a boundary between 2 different surfaces and bends through. There are 2 surfaces, there are 2 materials that have the same index, which means even though there's a boundary, it won't bend. Those 2 materials were the corn oil and the glycerol. I bit my tongue. I just bit my... That's super annoying. That's gonna bug me. The corn oil and glycerol, because they have the same index of refraction, if you had a layer of corn oil and a layer of glycerol, like sitting one on top of the other, and you shined a light down through them, you would not see any bend, because the speed doesn't change. The reason that that bend happens again is because the speed changes, right? Now, we can calculate how fast they go by using this equation, right? So, again, quick example. I'll do a quick example. I'll do it up here. Well, no, I'll do it off to the side. N equals C over V. So, simple version. calculate the speed of light in, I'll use glycerol. Glycerol. So I would say that N equals C over V. I know that the index of refraction for glycerol is 1.47. Right. Well, I'll call it V. I'll keep it as V. So the velocity of glycerol. Right. Now, in order to solve this, I need to multiply both sides by V, which means I get 1.47 times the velocity of glycerol equals 3 times 10 to the 8th meters per second. Then divide both sides by 1.47. The velocity through glycerol equals, no quick math here, not doing this in my head, no chance. 3 times 10 to the 8th power divided by, alright, so that is, I'm going to do approximately. It's approximately 2.04 times 10 to the 8th power. Now notice two things. One, this is slower. That should be true. It should be slower. You should never get a speed faster than the speed of light. The speed of light is a universal speed limit. You don't get to go faster than it. Video games, movies, you can go faster than light. Realistically, you're not going faster than light. It's not going to work. Meters per second. Forgot my units. Second thing, the exponent should be the same, right? You should get 10 to the 8th. But here's my speed. That's how fast light goes in glycerol. Right. The other thing that you might have to use the index of refraction for, and the other thing that this will tell you, is how much does it bend? What is the amount of bend that will take place? I'll use glycerol again. Right. So, if a light ray, you should notice I'm using the word ray now to describe a light wave. It's a wave. It's just like a single concentrated beam, right? So instead of seeing that constant squiggle, we're making a really big one. If a light ray reaches the surface separating air and glycerol at a 40-degree angle. What is the angle of refraction as it passes from air to glycerol? Right, and typically there will be a picture involved as well. So here's a surface. I have air on this side. I have glycerol on this side. The light ray is coming in like this, and they'll tell you that this angle is 40 degrees. And they want to know what's the new angle. Let me demonstrate that it's actually bending. Yeah. So the question is, what's that angle, right? And technically, like, is it smaller, is it bigger? So we'll do the math now. In order to do this, we have to use an equation that has two different indexes and two different angles. It's this equation here. Formally, this equation is called Snell's law. I don't think it's ever referenced by name. However, if you're doing an index of refraction, if they talk about refraction from one surface, from one medium to another medium, then you will use this equation, right? The equation is n1 sine theta 1 is n2 sine theta 2. So I'm just going to write that down. Now you don't need to memorize this because it's right there. You just need to recognize what each of these means. 1 is the original, 2 is the new one. So we're going from air to glycerol. Well, the index of refraction for air is 1.0. The original angle is 40 degrees. So that's going to equal N2, we said, was 1.47. Again, no units, just a modifier. And it's going to be sine theta 2. Now this might be math that you're not super familiar with per se. So I need to take both sides, divide by 1.47. So I'm going to leave all the numbers in for now. I know that multiplying by 1 does not actually do anything. I'm just going to leave the numbers in. Alright, so I'm going to get a number here. So I'm going to do sine of 40 divided by 1.47. Oop, just kidding. 1.47, that's better. So I have here that the sine of theta 2 is approximately equal to 0.43727 blah 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 stuff. That's not the answer. That's the sine. In order to figure out what is theta from here, right? If I want to solve for theta at this point, I need to take this number. I need to do the sine inverse of 0.43727 blah 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 blah, and that's going to equal theta 2, right? So if I do that number, then I get that my angle is about 26 degrees, which is accurate. That's what I drew. I kind of knew what was going to happen. So it's going to be a 26 degree angle, which means it's going to bend inwards, in towards that normal, towards the vertical, right? Generally speaking, low index of refraction, if you're going from low index to high index, it will bend towards the vertical. It'll bend towards the normal. Or theta will decrease. The opposite is also true. If you go from high to low, it'll bend away from the vertical. Or theta will increase. Right, opposites. So just like last year, lots of opposites. Now, in addition to this math, right, I can also do things. I can kind of go backwards and do things with this velocity. And the reason I can do things with this velocity is because I could now ask, or I can now say, what is the frequency of an X-ray as it goes through a different material? Right? That would be it's like a three-step question. That would be, I will admit, that would be a question I would have to write up, so it would look different from the others. If I asked you that question, you would have to solve for the speed of light through that material first, then plug into this equation. Alright, so just like we did the other day, when we did this, right, a sound wave has a frequency of something. What is its wavelength? Well, you knew that the speed of sound would be this. If instead I ask what's the wavelength of an X-ray as it travels through this material? Alright. If given that I give you the frequency, so an X-ray with a frequency of this travels through a material, what is its wavelength? You know the frequency. You would have to find the speed first, then you could solve for wavelength. Right? I can get a little more complicated. There will be some examples, there will be some practice questions on the new math. There will be some practice questions on identifying diffraction and identifying Doppler effect. They're pretty nice, they're pretty straightforward. There will be some questions on just reading the electromagnetic spectrum, reading what type of wave is or has this wavelength, what color light will you have if you have this frequency, so they will be very specific. And I can also ask questions now about what is the speed of light through this thing, what is the new angle as it refracts through something, right? So this new math that I did on this side. There will be example questions that will go up. You just took the little baby quiz on the first half of this, right? So you took the quiz on the stuff over here, right? The next thing that's going to happen is there's going to be basically a big test on waves, right? So the waves test will cover all of this. Right? It's in my opinion, it's not a ton of material. I think I went through a lot of it the first time, right? There's a lot more properties and such than the second time. Diffraction, Doppler effect, the extra velocity, and the refraction like calculations. I think they're not as difficult. I think they're not as scary. They're not as intimidating per se as some of the stuff that we did at the beginning of the year. We are going to double back to the beginning of the year soon because, again, waves was really the last big topic. Is there other stuff in the reference table? Yes, sure there is. Am I going to go over all of it? Honestly, no. Not all of it is incredibly interesting. So I will go backwards. We'll do some labs to remind you of some of the stuff that we did at the beginning of the year. But keep your eyes on MyCBA for practice questions with the new wave stuff. Keep your eye on MyCBA for when that test will take place. And make sure you remember that it's going to be on all of waves, and eyes on MyCBA for upcoming labs, right? Admittedly, the physics videos will probably be twice a week instead of just once a week, just because I change my mind a lot on what labs I want to do, especially since I didn't get to do a lot of labs originally, so I can have a tiny bit more freedom with how I do this one, all right? If you have questions, as always, please email me, set up a Zoom meeting, do something. Let me know that you have a question. Otherwise, I will assume that everything is fine. And until the next video, take care of yourselves, kids.